Hey, it's Mr. Shrum, and I'm picking up where we left off on the universal wave equation. Now we're solving for, we know the wavelength and we have a frequency. Now we're looking for speed. We're looking for V, the magnitude of the velocity for the wave. And the equation we'll be using is the universal wave equation. Wave speed equals the wavelength times the frequency. So, wham bam, substitute the numerical values. So the wavelength is 1.2 meters times the frequency, 3 hertz. Yeah, so 1.2 times 3, and that equals 3.6 meters per second. Easy peasy. So now in the next problem, we're looking for the wavelength. So we're going to rearrange the equation and solve for wavelength. So we know that V equals wavelength times frequency, but we have to rearrange that. Wavelength equals speed divided, well, velocity divided by frequency. Now we're just plugging in numbers. The speed, wave speed is equal to 350 meters per second, and the frequency is 880 hertz. And that gives us 0.4 meters. Now we're going to look at the velocity of a wave. Velocity of a wave. Recall the mechanical waves need a medium to propagate: air, water, a spring, or any other material. Each medium has a certain set of important properties that affect wave travel, including density, tension, temperature, stiffness, compressibility, and pressure. Any change in these properties of the medium might result in a change in the velocity of the wave. Note that all of these properties refer only to the medium through which the wave is moving. Frequency, wavelength, and amplitude are properties of the wave itself. Only the properties of the medium determine the velocity of a wave. None of the properties of a wave itself affect the velocity of the wave. The properties of waves help only to identify and compare various waves in a given medium. So they send you back to that simulation, keeping the frequency constant, and then increasing the damping force slowly. Okay, let's do that real quick. Oscillate, no end. Let's hide these meeting controls. We're gonna, okay, so we're gonna go to damping none, and then we're gonna slowly increase it. All right, do you know what's happening? So if you increase damping, the wave gets weaker and weaker the further away you get from the start. No damping. The wave is basically the same all throughout. Medium damping. You have this moving quite a bit, but then it weakens as you get further and further along. Lots of damping. Barely any energy is being passed. So what do we observe? The amplitude of the wave reduces as it travels. The greater damping force, lower the amplitude. Then it tells you to take a couple of measurements, yada, yada, yada. What do you observe about the velocity of the wave as you increase the damping force? The velocity of the wave remains constant for all values of the damping force. If you look here, they're all very close. And then part D, whether frequency might affect wave speed. What do you observe about the velocity of the wave as you increase the frequency? The velocity of the wave remains constant for all values of frequencies. And then it tests tension. When the tension is increased, the velocity of the wave is also increased. So really that's the only one that we've seen have any association with wavelength, or not wavelength, wave speed. The velocity of the wave seems to increase as tension is increased. You saw that increasing tension increases the velocity of the wave. Remember that tension is a property of a medium, not a wave. It is a common measurement in any linear, stretched medium, such as a string or a spring. It tells you how to experiment how tension affects the velocity of the wave. If you have a spring toy, you can attach it to a wall using a hook and hold the other end with your hand. Stretch the spring straight, but not too much, and then create a pulse along the spring. Stretch a little more and repeat the action several times. This type of hands-on experiment confirms the simulation results. If you increase the tension, that will increase the velocity of the wave. Note that tension only applies to strings, springs, cables, and other linear objects. Density in springs and in gases. The density of a medium is its mass divided by an appropriate length, area, or volume measure. For springs, we use a linear density like kilograms divided by meters, kilograms per meter. For liquid or gas, using a volumetric density like grams per milliliter or grams per liter for a gas. If you recall, the inertia is the tendency of an object to resist change in its motion. The molecules of a dense elastic medium will respond more slowly to the energy of an incoming wave than the molecules of a lighter spring or gas. As a result, a wave travels more slowly in a dense spring than in a lighter one, as the simulation demonstrated. Likewise, sound travels much faster in hydrogen air than in air, because hydrogen is less dense than air. But be careful. Density is not a good predictor of wave velocity beyond springs and gases. If, for example, you take liquid water, that is much denser than air, but sound travels more than 4 times faster through water than through air. All gases have the same compressibility and stiffness So it's easy to compare air to hydrogen. On the other hand, air and water have quite different intermolecular forces. Temperature in gases. Temperature is a measure of the average kinetic energy of a gas. As temperature goes up, the gas molecules are traveling faster and hitting each other more frequently with more force. As a result, the energy of a wave is transferred through a gas more quickly when the temperature goes up. For any given gas, such as hydrogen, oxygen, or the mixture called air, temperature is the only significant variable that affects the speed of sound waves. Velocity of sound is linearly related to temperature for any given gas. Other variables and other substances. Remember that a simple comparison of density is not a good way to predict the speed of a wave between two dissimilar materials. The same is true of temperature. Density, tension, temperature, stiffness, compressibility, and pressure are all properties of mediums, and all of these properties can affect wave velocity. It's most useful to know how these properties affect waves produced on springs and gases. For more complicated cases, such as comparing the speed of sound in liquid mercury versus water, the best source is a dependable scientific reference. But the main point to remember is that wave speed is dependent only on the properties of the medium itself, not on the properties of the wave. All right, so checkpoint question. The temperature of the air in a valley begins to increase after the sun comes up and heats the valley floor. What will happen to the velocity of sound in this valley? Oh, what do you think? Wave velocity and the temperature of the medium are directly proportional. So if temperature increases, velocity is going to increase as well. Now, what happens when you go from one medium to another? Imagine a wave is traveling from one rope to another one tied to it. When a wave reaches the boundary of the medium in which it is traveling, part of the wave is transmitted to the new medium and continues forward. Part of it goes back into the original medium. So this split has a special consequence for periodic waves. When a periodic wave reaches a boundary, a second rope, for instance, its frequency does not change, but the wave velocity does change in the new medium. The universal wave equation says that wave speed equals wavelength times frequency. So if the frequency stays the same and velocity changes, the wavelength must change in the new medium. Velocity and wavelength are directly proportional. So an increase in speed results in an increase in wavelength, and a decrease in speed results in a decrease in wavelength. Remember Janice at the ocean waves at the beginning of this lesson? She noticed that as the waves approached the shore, they slow down, the wavelengths become shorter, and those two effects are related. Damping makes the waves slow down in shallower water. The shallower the water, the slower the waves. This illustrates a gradual change in a medium's wave velocity. Think of it as a continuous boundary effect. This gradual change is common in the real world. So for instance, sound travels faster in warm air than in cold air. So sound waves that travel from a high, cold altitude will gradually speed up and increase in length as they reach the warmer temperature of a lower altitude. Another checkpoint. The sound of a loud warning siren travels through air and reaches the surface of a lake. The sound is then transmitted through the water at a speed about 4 times faster than through air. How will the frequency and wavelength in water compare to the same measurements in air? The wavelength will increase by a factor of 4, but the frequency will not change. The frequency of a transmitted wave stays the same, but the velocity is 4 times greater. The wavelength must also be 4 times greater because they're directly proportional. And that's the summary of the universal wave equation. We are using this equation to show a quantitative relationship between wave velocity, frequency, and wavelength. Mechanical waves, which require a medium in which to travel or transfer energy, are affected by properties of the medium itself. Temperature, tension, and density, for examples. The properties of the medium determine the velocity of a wave in that medium. Velocity is not affected by the wave properties of wavelength, frequency, or amplitude, which means that a bigger or longer wave will not travel faster in a given medium than a smaller, shorter wave. But a change in the medium can change the wave velocity, which in turn will change the wavelength. A wave changes when it leaves one medium and enters another. When it reaches the boundary of a new medium, the wave is partially transmitted into the new medium, and then part of it is reflected back into the old medium. The frequency of the wave remains constant in the new medium, but as the universal wave equation shows, the wavelength changes proportionally with a change in velocity. And that's it for the universal wave equation. If you have any more questions, message me in Canvas and I will help you out. But until next time, see you guys and stay safe.